2016, a long track inclined at angle theta and has small speed bumps on it. The bump are evenly spaced a distance d apart. Okay, so that's d apart. The track is actually moved much longer than shown, so I guess it's really long. So there's a bumps everywhere like this. Over 100 bumps. Okay, a car of mass m released from the rest at the top of the track. Student noticed that after reaching 40th bump, so this is 40th bump, 41st, 42nd, the car's average speed between successive bump no longer increased. This is interesting. So average speed between this is constant. Okay, that means before average speed is probably getting faster and faster each bumps. Once you reach 40, this average speed is constant, I guess, throughout after. Okay, this means the time interval taken to move from one bump to next bump becomes constant. Okay, so for example, if this takes 1 second, 1 second, 1 second, 1 second, probably here it should take longer. So maybe this takes 2 seconds, 1.8 seconds, something like this. And it came to like 1.1 second, maybe before 1.2 seconds. So basically this is time, okay, to 1.8. I'll just give you an example. And remember, this distance is constant. All right, sketch the velocity function of time moment it reaches 41 bumps and until 44. But the question says here average speed is constant. Okay, does not increase anymore. But what is average speed? So I was talking about v average. V average is usually, it's not v1 plus v2 over 2. This doesn't work. Okay, sometimes it works, sometimes it doesn't work. I'm not gonna go through like the mathematical detail of this, but I just want to talk about what is really v average. So if you have velocity time graph, let's say you have velocity of, let's say the graph looks something like this. Okay, then remember, area under this curve represents displacement. Okay, between 0 to sometime t, I'll just call it t naught. Now if you think about it, if you draw a certain line here, if you draw carefully, if I draw a line here, something like this, where if this area equals that area, you can actually say area of this green equals area of the blue. Okay, so that is what v average is. So that's what we are looking at. Sometimes this works. Okay, this v average actually becomes this if the velocity time graph was actually linear. If it's linear, and let's say this v1, this v2, then area of that equals area of like exactly midpoint, because this triangle cancels that triangle. In this case, this is v1 plus v2 over 2, because that's just the average of these 2 points. This only works, this equation actually, for v average only works if this velocity is linearly growing. Okay, but if the velocity is not linear, you can't really use this. Okay? Anyway, go back to this. So probably it's gonna look, before you reach point 1, so point 1, you get somehow velocity like this. Once you reach bump 41, this will reduce drastically. Actually, I want to make it bigger drop. So I'll use red. I'll use bigger drop like that. Then it increases until you reach, it increases the same rate. Probably it's like g sine theta of the acceleration. Then once you reach, it drops fast. Then it goes there, right? So you can see the pattern. But now, how do you write average speed? So once again, if the displacement is this air, okay, so between 41 and 42. Remember, this is 41 and 42. This is actually time. Okay, time it reached at 41, time it reached at 42. This area is displacement. That's the distance between the bumps, okay? And V average will be somewhere here, right in the middle. Okay. That way, area of this green equals area of this blue. Then you can say this is V average. In this scenario, because this is almost linear, except that portion, you can say that's like in the midpoint of the two if you want, okay? But I'm not gonna write that, okay, when I write the answer. I'll just say V average is here because area under the blue line equals area under the red line, which is the green arrow, in the green space, okay? Now, what happens, let's think about what happens before you reach this, okay? So what happens before you reach this? So this velocity time, and this time I'll choose downward direction as positive. So let's say this 0 bumps and first bump, start from 0 bumps, first bump, probably you increase like this, and when you reach there, it's gonna drop, right? That increase again, it drop, right? But it's not gonna be constant, okay? This will go up and up, something like this. This will go up and up. So that's bumps 2, bumps 3, bumps 4. This will keep going up until you reach bump 41, 42, bump 41. Okay, that's what real VT graph should look like. Okay, so once you reach 41, so 41, 42, 43, then your graph looks more like constant. Okay, it's gonna be constant from there. So that is what we call V average, because the question says it's actually maximum value V average. Okay, so that's what we're referring here. So here V average between these two would be there, but that's not maximum V average. Okay, so maximum V average will be this. All right, suppose the distance between the bump is increased but everything else stays the same. Is the maximum speed of the car now greater? What happened? The distance between bumps increased. That means you have more time to accelerate, right? So bumps close together. So in this case, this will be greater. So you have more time or more distance, doesn't really matter. So you have more time or distance to accelerate, right? Okay. And which bump return to original spacing, the track tilt greater angle theta is the maximum speed car greater or less than. So obviously that'll be also greater too, because you have acceleration is bigger, right? So bigger acceleration. So that will be also greater, right? All right, moving on. Before deriving an equation for quantity such as V average, it can be useful to come up with the equation blah 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 to try and find the V average. I think we're talking about V average max, right? Maximum V average between the bumps. The derivation can be checked later if it makes sense physically. Sira come up with the following equation for car's maximum average speed, blah blah blah. Where it says 5 minutes. So let's see if this makes sense. First part, okay, this constancy, okay, this there will be constant, I guess. But mass, I don't like this mass because usually mass does not play a role in speed. Okay, you remember usually acceleration doesn't have really mass. Okay? They actually cancel each other out. If you drop an object, heavy or light object in a vacuum, they reach same average speed or same speed, or they take same time to drop. So it shouldn't be mass dependent. And sine theta, okay, that makes sense because bigger the angle, you get the bigger the acceleration. That looks okay. How about D? If D is distance between the bumps, all right? Let's think about if D was infinite. If D was really, really, really long, then your velocity should shoot up, because if bumps, distance between two bumps is really large, it's basically just regular ramp, right? Then you'll accelerate as G sine theta. That means your velocity will linearly grow. So this will maybe go to infinity. So if D gets large, V has to get large too, okay? But not in this case, because if D gets large, V gets small. So I don't think that works, okay? The Taylor's equation, blah, blah, blah. So they did the experiment. That's a real weird experiment because you change mass and you look at average velocity. But So here they're vary mass and keep everything else same. So everything's constant except mass. The graph shows student plot, blah, blah, blah. This consistent with student equation, okay? Here, I don't care if this is correct or not. The question was, is this data consistent with the equation? Well, the only thing changed was this mass. So basically, the average for student equation was C G sine theta over D, but this is all constant, okay? In this experiment, the only thing changed is M. So it's like y equals, y equals mx graph. This is the average, this mass. Then you should get a graph like this, because so y-intercept has to be 0, u has to be linearly growing, right? So is it consistent? I'll say no, because it looks something like, how do I draw a linear line if you draw a linear line? Well, this is arguable. Can you say these points are linear? If you can say that's linear, that's consistent, but it does not go through, it does not go through y-intercept of 0. So does it consistent? I'll say it's no, because it's not, it deviates from linear equation, okay? And it does not go through y-intercept of 0. That's how I'm gonna explain, okay? Another student suggests that whether or not data above are consistent with the equation incorrect for other regions, does the equation make sense? So other region means not mass, except what's the other region? And I think I already mentioned that. One is, I'll just say D, right? So does the equation, so answer is no, because if D gets large, you get more time, you get more distance to accelerate, so V average should go up. Or if you look at the extreme case, if D goes to infinity, it's basically a ramp with, I'll just say bomb set here and at the end. So that means velocity acceleration will be g sine theta. Then velocity will grow linearly with slope of g sine theta. So it's gonna go up like this. So the average will also go up. So that's somehow I can explain. Okay? And you should elaborate. All right, that was it.